We're going to be focused on projectiles that are launched horizontally. That means we're going to have something and it's going to have an initial velocity pointing left or right, something like that. First, to be able to do that though, we need to look at this projectile which is just dropped, and we want to know how much time will it take this ball to hit the ground, and we want to know what velocity it has when it hits the ground. So standard deal, we're going to use our suvat. Now you can decide which direction you'd like to make positive. I'm going to make upwards positive, but you might find it easier to make downwards positive for this question. If upwards is positive, the 25 meters downwards that this ball is going to travel needs to be negative. If it's dropped, its initial velocity is going to be 0. We don't know its final velocity, that's something we want to find, but we do know its acceleration. And we also want to find t. So let's find v first. We know v squared equals u squared plus 2as. So v is going to be the square root of u squared plus 2as. Needs to be negative square root because the velocity will be pointing downwards if you use the same sign convention I did. So u is 0 squared plus 2 times negative 9.8 times negative 25. So those negatives cancel there, but the negative out the front doesn't. Okay, 2 times 9.8 times 25. So there we get a velocity. We already have the negative sign there. So if we did that to 2 sig figs, it'd be 22 meters per second. And that represents downwards here, and that makes sense. When the ball hits the ground, its velocity is very much, well, imagine a nanosecond before the ball hits the ground. The velocity is very much downwards. Okay, if we want to find t, we could use s equals ut plus a half at squared. Doesn't matter that there's two t's in this equation because u equals 0 here. So we're going to have ut will be 0, so we're just going to have half at squared. If we rearrange this for t, we need to multiply both sides by 2, divide by a. I've just swapped around the left and right there, and we're going to take the square root. And for time, we always take the positive square root. So we can have 2 times that displacement divided by the acceleration. And that's inside of that square root. I'm not typing the negatives into my calc, although you're more than welcome to, because I can see that they're going to cancel each other out. So there we get to 2 sig figs, 2.3 seconds. Cool. Now, how does this relate to the next question? What an excellent question you have. We've got a similar situation. We've got the ball, it's 25 meters from the ground, but now it's traveling 10 meters per second to the right. We're interested in how far the ball travels, and it's talking about this distance here. So it is talking horizontally here. Often it would say something like, how far horizontally does it travel, or how far, can't think of another way it's expressed. We'll look at some exam questions, but something to indicate along the ground or as the bird flies. It's not asking you to calculate the distance it travels through the air, like the distance of the parabolic path. That would require some calculus that is not on the course. So we know that this situation vertically is exactly the same as this situation that we had up here. This situation has the same vertical information, so that means if it takes 2.3 seconds for this ball to hit the ground, it's also going to take 2.3 seconds for this ball to hit the ground. This information here, as I said, is vertically the same. So now, when we're doing projectile motion stuff, we're going to have 2 separate columns. We're going to have vertical information and we're going to have horizontal information. So horizontally now, we need horizontal information because we're interested in this distance that we're traveling along the ground, s. Now horizontally, there's only 3 things you can know. You can know its displacement, you can know its velocity, and you can know its time. Because remember, the velocity doesn't change for projectiles horizontally. There's no force to change that direction or speed. So s is what we're trying to find. V is 10 meters per second, the entirety of this ball's journey, horizontally though. Its vertical velocity changes, but its horizontal velocity is unchanged. The time we found before, let's just use the rounded amount of 2.3 seconds. Velocity equals displacement over time. So that means displacement will be velocity times time. So I've got the velocity of 10 meters per second times 2.3 seconds, so it's about 23 meters. Really handy to be able to use this equation, velocity equals displacement over time. We can only use that in circumstances where velocity is constant. That is true of the horizontal information here. So, some tips and tricks for when we do two-dimensional problems. You're going to start with SUVAT in the vertical direction 99% of the time and pretend it's just a free-fall problem that we've had in the past. Because we can treat the vertical and horizontal components separately, with time being the thing that links the two, that works just fine. The air time is the same for horizontal motion. So just like we used before, we knew it took 2.3 seconds for this object to hit the ground from 25 meters up. And that 2.3 seconds links the horizontal and the vertical motion. So we use that for both. And horizontally, we can use V equals displacement over time, and that works quite well. But you still got to use your SUVAT equations for vertical stuff. So let's look at some more examples. We've got a daredevil diver is jumping off a cliff. They wish to dive safely into the water. That's good. There are rocks underneath, so the diver knows they must push horizontally off the cliff to avoid them. How long does it take them to reach the water? Okay, so here's your plan of attack. You have two bits of information here. You know that this diver has to travel 35 meters downwards vertically and 5 meters across horizontally. If you thought just of horizontal information, velocity, displacement, and time are the three things you can know. Unfortunately, you don't know this person's velocity and you don't know the time. So you've only got one known and two unknowns. If instead you look vertically, like our strategy up here suggested, you know more information. So let's do a little heading vertically. We're going to do our S, U, V, A, T. Yes, it did bother me that I didn't hit it on those lines. I was trying to be compact and then I immediately regretted it. So perhaps let's make, for this question, let's make downwards positive and let's make to the left positive. You, of course, could choose a different sign convention. So long as you're consistent, you'll get the same result. So that means we're traveling downwards 35 meters, so we can make that positive. So with this question, they are launching themselves horizontally off the cliff. That means the vertical component of their velocity is going to be 0 initially. So they're not pushing themselves upwards or downwards. Their velocity is entirely horizontal. That means there's no vertical component, therefore it's 0. We don't know the velocity and we're not interested in finding it for this question. We're asked how long does it take, so we're looking for time. And the acceleration is 9.8. I've made it positive in this question because I said downwards is positive. So we want an equation linking S, U, A, and T. S equals UT plus half AT squared is going to work quite nicely here because UT is going to be 0 because U was 0. So S will be half AT squared. T is going to be 2S on A and take the square root. So 2 times 35 on 9.8. Notice if you'd said upwards was positive, you would have had 2 times negative 35 divided by negative 9.8, and you get the same result as I'll get. So we have 2 times 35 on 9.8. Okay, so we get what would be appropriate sig fig wise. 2 would work, so let's do 2.7 seconds. Now in part B, we're now asked about horizontal information. What horizontal velocity do they need to have when they push off from the top of the cliff? So we now know from part A, at this point here, the time is 2.7 seconds. That's how long it takes them to travel this vertical distance. That links to the horizontal information. That is the exact same time it takes to travel this horizontal distance. So remember before we were talking about the fact we only had one piece of information horizontally? Now we have 2 because we use the vertical information to find out stuff about time, and that's the strategy. So you can know the velocity, displacement, or time. Displacement is 5 because we said that was in the positive direction and it's 5 meters from that cliff there. Velocity we don't know, that's what we're trying to find, and the time is 2.7. Because we're in part B, And in part A, we found 2.7. You're perfectly fine now and in the exam to use that rounded answer. If you use the unrounded answer, that's also okay. It's more effort here. If you were to use that time for another calculation in this question though, so if you found the time and you needed that to find something else as part A, don't round it off then. Keep the full number. So when you're going from one question part to another that you can round like this. Okay, velocity is displacement over time. So that's 5.0 on 2.7. Okay, so we get 1.9 meters per second. It does say horizontal velocity. It doesn't just say magnitude. So we should say something like to the left. We know it's to the left, 1, because we looked at the diagram, and 2, because our answer was positive, and we said to the left is positive. Now, the next one, part C, it says, what is their horizontal velocity when they hit the water? The important thing to remember is the horizontal velocity doesn't change. U equals V, and I'm talking specifically horizontally, equals, well, not really equals, but it is a constant. So that means that 1.9 meters per second to the left is constant. I like this little diagram here. It shows that if we turn gravity off, so we didn't have to look at the vertical components of the motion, it travels the same distance each unit of time. So yeah, another nice compelling reason why the horizontal velocity remains unchanged. Okay, let's look at the next bit. It says, what is their vertical velocity when they hit the water? Okay, so our final point is going to be at the water again, and we're really using this information another time. So let's write that down over here. So vertically, as a reminder, I said vertically downwards was positive, S-U-T. We said S was 35, U was 0. We're interested in finding V, and we know A was 9.8. Now you could put in T equals 2.7 here, but ideally you use the values that they've already given you because it means you're not worrying about having rounded off an answer. So if we use V squared equals U squared plus 2AS, V, we need the negative. With V, when that projectile hits the water, the vertical velocity, let's write V vertical, it's going to be downwards. So that means when we take the square root, we're going to make it positive because we said downwards was positive here. So we're going to have U squared plus 2AS. Conveniently use 0, so we've got 2, 9.8, and 35. I always make my square root sign slightly too small. So now we'll have 2 times 9.8 times 35. Okay, so we get about 26 meters per second. Now part E is asking what is their total velocity when they hit the water and the angle they hit the water at. When they hit the water, they have two velocities going on there. They had what we just found, let's just use the rounded amount, 26 meters per second. And they also had that constant velocity that we found in the previous question, 1.9 meters per second. What we can do is we can create a triangle with these. So to do that, we'll move this one over here. And then what we're trying to find is this length here. This length gives the total velocity. To find that, we're going to have to use Pythagoras. So V total is going to be the square root of V horizontal squared plus V vertical squared. We had V horizontal, that was 1.9, and we'll square it, plus V vertical, 26, square it. Okay, oops, oh well, I can still fix it, there we go. So that means the total velocity there, let's do it to 3 sig figs just for fun. You can do it to 2 if you like, but then it looks like 26.1 meters. If you do it to 2 sig figs, it does kind of look like that the total velocity is 26, which is the same as the vertical. So doing it to 3 isn't bad here to notice that it is in fact different. So really handy there. We could also find this angle here. So we could say the angle from the vertical, they haven't specified. So that angle, we could do tan theta equals the opposite over the adjacent. So we'll need inverse tan. The opposite side length was 1.9 and the adjacent side length was 26. So we've got 1.9 on 26. Okay, so we get, let's say, 4.2 degrees from the vertical. So that's a really helpful solution strategy when looking at projectiles launched horizontally. The vertical component of the velocity is initially 0, and it is going to increase in magnitude as it falls towards the ground or whatever we're looking at there. What you're going to be looking at next is projectiles launched at an angle. And that one's interesting because the vertical and horizontal components of the velocity will not be 0 initially. So it involves another step up in what we're doing here.